So I want to talk today about, first of all, the idea of a universal mapping property. Universal mapping property is a way of using the language of category theory to give a characterization or definition or specification of a structure or structured object in a way that's unique up to isomorphism. It picks out a certain kind of structure in terms of its mappings to other objects in a category. So the simplest example, or well, maybe the first example historically of such a thing, is the definition of a product of two objects in a category that was given by McLean in 1949 or something like that. So we'll start with that. Well defined. So in any category, a product of objects A and B consists of the following. Well, an object, which I'll for the moment write P, equipped with arrows to A and to B, with the following universal mapping property. Given any object X and any arrows into A and to B, there exists a unique map U from X into P, making the two triangles commute. So let's, in order to write that down, let's give these things some names. So I'll call this one P1 and this one P2. And now the idea is that this structure here is a product, just in case, given any X and F1 and F2 as indicated, there exists a unique map U, that's this one, such that P1 after U is F1 and P2 after U is F2. So, and now just a little bit of notation. When we have a product like that, we usually write P with the usual Cartesian product notation, and we call these things the projections. P1, P2 are called projections. And then we write the unique map U, determined by F1 and F2, in the form F1, F2, using the pairing notation. And then the equations become P1 of F1, F2 is F1, so that's the familiar projection equations. F2 is F2. Okay, so that's the idea of defining a product in terms of mappings to, and in this case from, other objects in the category. Let's look at some examples. Well, first of all, let's have a basic result about products. I said that these universal mapping properties determine things uniquely up to isomorphism, so let's just check. Fact, products are unique up to isomorphism. Products are unique up to isom. So what does that mean? Well, let's suppose I have here A and B, and I have two products. So what I want to say is, if I have two different products, like this one and this other one here, well, then they must be isomorphic. So that's my claim. Okay? Any two products are isomorphic. So let's see how to prove that. We'll take one here, say A cross B, with its two projections, P1 and P2. And let's take another one here, A cross B, with its two projections. We'll call them Q1 and Q2. And now, if this one is a product, then this is some object with a pair of arrows. Then there must be a unique arrow here, namely P1, P2. And if this one is a product, let's rewrite it down here. Nope, P1, P2. If this one is a product, then because this has a pair of arrows, there must be a unique map here, Q1, Q2, making these two triangles commute. And now let's see what happens if we compose these two arrows with each other, okay? So if I compose these two arrows like this, and then I take the follow that with the projection by P1, well then because this triangle commutes, that's the same as just going across here. Yeah? So going down and across here is the same as going like that. But now this triangle commutes, and so that's the same as this. Right? So the whole thing composed with P1 is P1. And similarly over on this side, the whole thing composed with P2 is just P2. Yeah? And so the whole map coming all the way down here is just the pair P1, P2, P2 on A cross B. Yeah? However, the identity map from A cross B to itself also has that property. Right? And so it follows that this must be the same as the identity on A cross B. Because if I put the identity map in here and compose it with P1, I'll get P1. If I put the identity map here and compose it with P2, I'll get P2. And by the uniqueness clause, which is right here, right, this uniqueness part, this vertical composite must be the identity. And so I've shown that the composite of these two maps is the identity on A cross B. But of course, the whole argument is symmetric. So if I do it the other way around, I get the identity on A cross prime B prime. And so I have an isomorphism between the two. Yeah. I have maps going back and forth, the composites of which in each case are the identity maps. So that, yep?
Is the uniqueness of that definition, or is that derived?
That's the definition of a product.
Okay, thanks.
In that sense, the universal mapping property characterizes this structure uniquely up to isomorphism. Right? Any other structure with that same property will be isomorphic to this one. So let's look at some examples of products. So for example, well, of course, in the category, so not every category has products, right? And some categories might have products for some objects, but not for others. But lots of familiar categories always have products for any two objects. So in sets, the product of two sets is just the Cartesian product. That is, the set of all ordered pairs, and let me write curly parens here to distinguish between these things and my pairing operation there, with A an element of A and B an element of B. So in the usual set theoretic construction of Cartesian products out of ordered pairs, this set of all ordered pairs, together with the usual projections pi 1 and pi 2, is a product in this sense. So it's uniquely determined up to isomorphism by that property. And it doesn't really matter how you define this pairing. There are lots of different ways of defining pairing in set theory, and any one that you choose will give a product, categorical product in this sense. Similarly, in topological spaces, in posets, you have the usual products of structures. So let's look at posets, for example. If I have two posets, P and Q, I take the product poset. That's going to be, well, the underlying set will just be pairs like this, and then I'll order those pairs by saying PQ is less than or equal to P prime, Q prime, just in case. And then I put the product ordering on there. So I say P is less than or equal to P prime in P, and Q is less than or equal to Q prime in Q. And then what I have to check is, yep?
Also do an OR?
No.
Okay. For like lexicographic ordering.
You could order this in lots of different ways, but I claim it won't give you a product in the category. And that's the interesting thing here is we have this definition that tells us what a product has got to be, right? And so that serves as a guide for how to order these things. There are lots of different ways of putting an ordering on this set, right? And they will give you different orders, different posets. But in order to actually make it be a product in the category, there's only one way, up to isomorphism on posets. And so what we have to do is we have to check that this particular specification is the one we want, and that means checking that it has this universal mapping property in the category of posets, which I'm going to do right now after I answer this question.
I'm confused about P1 and P2. They look like arrows, but Are they, is that part of the existential thing, that there exists a U and a P1 and a P2, or where are they?
So a product of objects A and B consists of a triple,
Okay.
P, P1, and P2, such that for all. One way of thinking of it is, it's a universal gadget of this form. Okay? So give it a map, an object equipped with two maps, one to A and one to B. So it's one of these, and every other one maps into it. Unique. It's a universal such gadget. That's the structure is the whole thing. Yep.
That's a related question about just the diagram notation.
Yeah.
So how much, so the diagram is a kind of slightly informal picture of the more exact thing on the right.
Yeah.
Which parts of the stuff on the right are missing from the diagram?
You mean in terms of the
So how much of
rendering or something like that?
How much of the stuff on the right could we uniquely read off if we weren't given it and we were just given the diagram?
I don't think you can't recover the whole thing because you need the order in which these arrows are drawn.
Exactly, and
Right.
also the bang is missing, right?
The uniqueness, yeah. I mean, the custom is this dotted arrow means there exists a unique thing, given the rest of the problem. So, I mean, I guess you could say, here, the product of these objects is this part, so that's kind of given first. And then you have to say, somehow, for all things like this, there exists a unique one.
So once you drew the PP1 to 2, the rest pretty much falls.
I guess. I mean, in general, the universal mapping property is going to be something of the form, it's a gadget of this structure, which is universal, in the sense that given any other gadget of that structure, and now you have to know to map into it or map out of it. There are left and right variants. Okay, so let's just see that this is really a product. Category of post sets, just to kind of see what's going on here. Here's P1 and here's P2. Well, first of all, we have to check that these projections are monotone to make sure that this really is an object in the category of post sets. But that's, by the way I've defined this, they're obviously monotone, right? Because if this is less than this, then each of the projections is also going to stand in the relation. So that's a good diagram in the category of post sets. And now I say, give me some other post set and a pair of monotone maps, F and G. How am I going to find this thing? Well, what I'll do is I'll just take the set theoretic pairing, the pairing function, F and G, right, which I know exists because of this case, because I have products. And the underlying set here is just the product in the category of sets. And then I just have to check that this thing is monotone when I define it in that way. So I need to check that the map FG is monotone. So for example, if I have x less than or equal to y, I need to check that this is less than or equal to f g y for x less than or equal to y in the post set x. But what is this? That's just the pair fx gx, and this is the pair fy gy. And now when is this thing less than or equal to that? Well, just in case f of x is less than or equal to f of y, and g of x is less than or equal to g of y, but that follows from the fact that f is monotone and the fact that g is monotone. So the diagram I started with was in post sets, and so f and g are monotone, and therefore this map is monotone. So that thing gives me, and now I've checked that it has the universal mapping property, so I know this is the right way to order the post set. Thanks for that question. That really came in handy. All right, so that's an example. And there are lots of other examples. I won't go through them, but I'll just mention some. For example, in cat, we could wonder, does cat have products? Well, I would have to find for a category C and a category D a way of making a new category, a product category, with a couple of projections down to the individual categories. Anybody have any ideas? This was an example, the first example that I gave last time of a construction of new categories out of old. So last time I showed you how to make a product category. Nobody complained and said, why is that the product? It just looks kind of product-y, right? But now we know that it was right. At least once we check that it has this universal mapping property, Remember this category I defined? The objects were pairs, C, D, and the arrows were pairs of arrows. That category has this universal mapping property, and that tells us we defined it in the right way. Right? It's a way of checking that you're doing things right, so to speak. So that was an example. Another example is, well, actually this one restricts down to this one, right? Remember we had these two aspects, or two dimensions of the notion of a category, the poset dimension and the monoid or group type dimension. We have lots of arrows and few objects, lots of objects and few arrows. So this is just a specialization of that to the posets. And of course there's another specialization to monoids or groups. So in monoids or groups, you get the usual notion of a product monoid or product group, just like in your algebra course. If you had an algebra course and you defined a product of two groups, that will give you exactly this, this notion. You'll find that you check the universal mapping property, and it's a product in the category of monoids or in the category of groups. Let's try an example of a different kind. Let's take P, a specific poset. So we're not looking at a product in the category of posets, but we're looking at a product in a poset. Okay? So I want to say, let's have some, the elements of the poset, I'll write them like this, say X, Y, Z. These are all elements of the poset P, and the poset has an ordering relation, X less than or equal to Y, etc. Right? And now, what would it mean to have a product in the poset? Well, sometimes it's good to think of a poset like this as a big egg, right? And the ordering goes up. And if there is a least element, it's down here, and if there's a greatest one, it's up here, but there doesn't have to be. But in any case, the ordering is going like this. So here's X and Y, for example, and now I want to know what would it mean to have a product of X and Y. So it would have to be something here, X cross Y, and it would have to have maps into X and into Y. So in this case, that's the ordering, so it means less than or equal to here, less than or equal to here. There. So X cross Y is less than or equal to X, and X cross Y is less than or equal to Y. And moreover, it has the property that if anything Z, let me just write lines here, is less than or equal to X and less than or equal to Y, then it's less than or equal to X cross Y, where the uniqueness is automatic now because we're in a poset. So that means, so here, let's just rewrite it here. If Z is less than or equal to X, and Z is less than or equal to Y, then Z is less than or equal to X cross Y. Well, of course, if Z is less than or equal to X cross Y, and X cross Y is less than or equal to X, then Z is also less than or equal to X by transitivity. Yeah? And similarly over here for Y. So this rule, using that fact, this rule goes both ways. This is an if and only if. It says that for any Z, Z is less than or equal to this thing, just in case it's less than or equal to both of them. Anybody recognize what that's saying? X cross Y, I should have used A and B or something. The cross there is interfering. X cross Y is what? Greatest lower bound? Greatest lower bound. Greatest lower bound of X and Y. Usually written like that with a meet sign. Meet. Or conjunction. Yeah? So the conjunction of two formulas, or the meet of two elements in a poset, like in a meet semilattice, is exactly the product in this setting of posets. Okay? It gives us, we take this definition, we specialize it to a category that happens to be a poset, and we recover the usual definition of a meet in a poset. Good? So we have a kind of unifying thing going on here, right? There was something else I wanted to say before we go on.
So what was the categorical generalization of being double bound being stuff?
That was the next thing I was going to say. Thanks. So let's do this. Let's say, here's an example of duality. Is that the next thing I want to do? Sure, I could do that next. It fits. What is duality? Sorry, what?
Case, the product is only defined if meats actually exist.
Well, that's always the case. In any category, the product is a specification or definition, but it doesn't have to exist.
Okay, so this construction does not work for each POSET.
In general, the definition of a product does not work for each category.
And I guess what we're saying is it doesn't even work for each POSET category.
It's not a construction, it's a specification.
It's a specification, it's a definition of what it means to be a product. Or here it's a definition of what it means to be a meat in a POSET. This is the definition of what it means to be a meat. A POSET in which any two elements has a meat, in this sense, is a meat semilattice.
Yes.
Okay? So it's not a construction of the meat, it's a definition of what it means to be a meat.
Okay, but in the case of the sets, it pretty much looks like a specification.
What?
In the case of the sets there above, pretty much...
So this is a proof that sets has products.
Okay.
Okay?
And you prove that by giving a construction.
Yeah, so there I've shown that sets has products. And similarly, the category of POSETs has products by constructing such a thing. It satisfies the universal mapping property. So in a POSET, a meat product is a meat, and then we can define a POSET is a meat semilattice. I haven't proven that the laws for meat semilattices hold just from the existence of product, but it's true. If and only if meat semilattice, if and only if POSET P is a meat semilattice, if and only if P has a product, A, B, or all A, B, or P. Does it make sense now?
Yes.
Okay. Now you can check that if you have a product for any two elements, that the product necessarily satisfies all the laws for a meat semilattice. It's associative, it's commutative, and so on. Okay, I think that's it actually. It's associative and commutative. Good. So here, duality. What is a coproduct? Well, so that's kind of a cheating, isn't it? I already told you coproduct. Coproduct means, well, just by general rules of concept formation in category theory, you add the prefix co to mean it's a product in the opposite category. So let's do it like this. So we take a category C and we say the coproduct in C, that equals in C op a product. So let's do it like this. We have an object, which I might just as well start writing as a coproduct like this. And now it's equipped with a pair of maps into it rather than out of it because we're working in the opposite category. And it's the universal such thing. So that means given any other object and a pair of maps into it from these guys, there's a universal thing here, making these guys commute. So that's exactly the definition that I just gave you for a product, except I've reversed all the arrows. Yep?
Is there a terminology for just the two arrows?
So just like here, there are some conventions. We write this plus sign for coproduct. We write this thing sometimes as the maybe with a square bracket or something. That's one customary way of writing that thing. And we call these things I1 and I2 the injections rather than projections. Okay, so that's the customary jargon. Okay.
Have universal property? Yes. Sort of a general name for just three objects and arrows going from the outside to the inside.
Co-span.
Co-span. Okay.
So we know
By duality that, so we know that when they exist, coproducts are unique up to isomorphism. I don't have to repeat that argument, right? I could take that, if I wanted to, I could take that argument, turn all the arrows around, and I would get another argument that proves that coproducts are unique up to isomorphism. That's the idea of duality. I only have to do the proof once, yeah? And then I know the same thing holds for the dual case. So here's another thing. For example, let's show whenever I have a product of two objects in a category, there's a canonical isomorphism between these objects like that. So products are commutative up to isomorphism. What's the canonical map going from here to here? Well, it's the pair, so any map into here is going to be written as a pair. It's the pair P2, P1. It's a kind of a twist there, right? Just twist the order, and that gives me a map here. And going back here, you can do the same thing. Yep. So you can check that that's an isomorphism. It's a simple diagram chase like that. It shows that this thing is an isomorphism. And then it follows by duality. The coproducts are also commutative up to isomorphism. Similarly, products are associative up to isomorphism. This, I think, is a homework exercise. A cross B. And so again, by duality, the same thing is true for coproducts. They're unique up to isomorphism. What are some examples of coproducts? So coproducts. What about in sets, a coproduct of two sets? That's the disjoint union. Disjoint union. How do you build the disjoint union of two sets? It doesn't matter as long as it's disjoint. It'll have the universal mapping property, right? There are lots of different specifications. You could say, well, just take A union B if it happens that they don't have any intersection. That would be a disjoint union. But what if they do have an intersection? Well, then move one out of the way by taking a copy of it, or put in some tags. Tag this one with everything in here with a 0 and everything in here with a 1, right? So that's a kind of usual way you could say it's a bunch of pairs of the form x, comma, delta, where x is in like that, is in A if delta equals 0, and x is in B if delta equals 1. You know what I mean by that, right? So that was another way of making a disjoint union. There are lots of other ways. It doesn't matter as long as you get the union to be disjoint. In posets, in topological spaces, the coproducts exist and they're built in a similar way in cat. However, in groups and monoids, they're more complicated. Groups, more complicated. Sometimes you see these things written in the form of a tensor product because you have to kind of take the operations into account and do some extra stuff. Okay, what about in a poset P? What do you suppose the coproduct is in a poset P? Here's our picture again. So here was x, here was y, and now it's going to be something up here, x something y plus y. It's going to go like that, and then for any z up here, right, there's going to be something like that. And then we'll have, just by duality, we'll have exactly this same rule. It'll satisfy the property that if x is less than or equal to z and y is less than or equal to z, then this new thing, x plus y, will be less than or equal to z, and conversely. Okay, so that's a least upper bound, and it's usually written as a join. That's what you expect, I suppose. Right? So all of the things follow from basically one and the same universal mapping property, just putting it into different settings. Okay, so that's that. Now here's a more interesting or different kind of universal mapping property. Maybe I need a new board for this. Well, I'll do it right here. Oh, here, let's put a fact here. So I already said over here, the joins, if they exist, the products, if they exist, are meets in the sense of a meet semilattice, and the coproducts, if they exist, are joins in the sense of a join semilattice. That means they're associative and commutative. But I guess we already showed that, right, up here. So that's the exercise that I gave you before to check that those things hold. We just checked it right there. Okay, so here's another kind of universal mapping property. This is the notion of an exponential. And it's a kind of compound thing because it's defined in terms of something else that's already been defined, namely it's defined in terms of a product. Okay? So let's suppose we have, suppose the category C has all products. That means for any two objects, I can find a product diagram. Okay? Then I'll define the exponential like this. So for A and B, an exponential is a structure of the following shape. First of all, it's an object, which I'll write like that, B to the A, together with a map across A. That's where I use the product. A map down to B, which I'll call epsilon. And now it has the following universal mapping property. If you give me anything of that same shape, some F here, mapping into B from a product with A, then there's a unique F bar such that when I put that into this diagram right here, the triangle commutes. And how do I put that into the diagram? Well, I take F bar and I cross it with the identity on A. I haven't shown you how to make a product of maps. I've only shown you how to make a product of objects. So let me do that quickly. And then that will complete the definition of this universal mapping property. So just to write it down here, it says, I have a structure of this form. And then it says for all x and for all f, there's a unique f bar of that shape such that epsilon of f bar crossed with 1a equals the f that I started with. So how do I make a product? Really, let's observe that product is a functor. So in this circumstance, right? So let's say if C is a category with products, if C has products, binary products, by which I mean any two objects have a binary product, then there's a functor product functor going from C across C into C, and it works like this. It takes a pair of objects here, A and B, that's an object in this category, to their product, and then it takes an arrow, so let's do it like this. So what's an arrow there? Well, it's a pair F, G, like that. It's got to go to A cross B. And now I have to have an arrow right here, right? And that's the arrow that I'll write, F cross G. And how does it work? Well, I put in the projections here. I'll just do one side and you'll get the idea how to do the other side. And then here I put in G, right? I do the same thing over here for F. And now I compose through, and that gives me a map from here down to B, B prime, and similarly there's a map down here over to A prime, and so I pair them up. So this is the pair of F after P1, G after P2. This is P1 and that's P2. So the left-hand side there is implicit P2. Make sense? No, it doesn't make sense. Okay, I'll fill in the rest of the diagram then. Here's F. Here's A prime. These are the Q's, Q1, Q2. I'm not even using those. Okay? So this is the value of this functor on the pair F and G. It goes to this map. The product functor applied to Fg is this map F cross G, which I just defined here to be the pair Fp1